So another way of writing 2 to the negative x was 1/2 to the x. So 2 to the x was growth, and 2 to the negative x, or 1/2 to the x, was decay. Okay, so when I look at these next problems, A says, state whether it represents growth or decay. Now, we're going to talk about the end behavior in a second. Don't worry about that. Growth or decay? 3 to the x. Growth. In fact, 3 to the x is going to look exactly like 2 to the x. It's going to be a little bit steeper, but for our purposes, it's going to be exactly the same. This is a growth curve, and that's the 0.01, and this is the asymptote when equals 0. Okay? Now, what about 3 to the negative x?
Decay.
That will be decay, and that one will have the same intercept and the same asymptote, but it's going to be coming down like this. All right. What about 1/2 to the x?
Decay.
Decay. Now, be careful with this one. This is 0.75, which I'm going to go ahead and write as 3/4 to the negative x, which would be the same as 4/3 to the positive x. That's a growth. So here's the deal. Numbers less than 1 will be decay. Negative exponents will be decay. But when you have both of those things, they like cancel each other out, and it actually becomes a growth. Got it? Now, every growth is going to have that shape. Every decay is going to have that shape. So, when we describe the end behavior for every exponential growth problem is going to be the same. Remember that our end behavior, we talked about this before, is expressed as 2 limits. One with x going positive and one with x going negative. Now, let's look at our growth problem. As we go to the right, as x gets big, what is happening to y?
Goes to positive.
Positive infinity. It's just shooting up into space. As we go to the left, though, what is happening to our curve?
It is going down.
It's going down, but it's not going down. It's not going down like this down.
Yeah.
It's getting closer and closer to
1 or 0.
0 from the top. It's coming down, getting closer to 0, approaching from the top side. Now, for your decay curve, what happens with your end behavior? Every decay is going to have the same end behavior. Every growth is going to have the same end behavior. What is it for a decay? As you go to the right, what's happening? Closer to 0, right, from the top? And what happens as we go to the left? On a decay problem, we're going to the left, and it is going up. Is it going up? Without any ceiling, right? You just keep going up. So, the end behavior for every growth, exponential growth problem, will be the same, because this is what the picture will look like. And for decay, same thing. That's what the picture is going to look like. So I can just see my sneaky little self saying to you, describe the end behavior of that. What is the first thing you're going to do if you're going to answer that question? You got to figure out which of those is. That's right. Is it a growth or a decay? Well, when you see that 2/3 right there, I hope you're thinking decay. So the end behavior would be right here, because that's what the end behavior of the decay function is. Got it?
Yep.
All right, because now, number 6 is all about different functions. These are clearly not exponential. These guys are logistic. So our logistic functions are going to be of the form a over 1 plus bc to the x. You might want to just write that down over in the margin. We don't need it just yet, but we're going to need that in a couple days when we start writing these equations. So if your equation has that form, which these all do, if you look at them, the a, the b, and the c can be different numbers, and they are in all of these. That's logistic. This is one of your logistic functions. Now, that's one of your BFFs. Do you remember that that's the one that looks like this? Do you remember that? That's your logistic function. Okay, so what you're going to do now is take this logistic function and you're going to figure out this point and these two. So y equals what? Y equals what? The asymptotes and the y-intercept. You're going to figure that out. Well, the y-intercept is simple. How do you find the y-intercept of anything? No matter what. Plug in 0. So if you plug in 0, okay, Eli, I'm plugging in 0 right here. So 0.8 to the 0 is 1, but it's times 2, so 2 plus 1, 3, 12 divided by 4. So your y-intercept is at 4. Now, please understand, the y-intercept will not necessarily be halfway between your asymptotes, okay? It is where it is. In this case, it's at 4. Now, to find the asymptotes, would you agree the asymptotes are like the end behavior? This is going up, but it's getting closer and closer to something. That would be the end behavior. And end behavior, remember, happens as x gets really, really big. So I want you to think about this for a second. X is getting really, really big. Really big. What happens to 0.8 when you raise it to a really big power? And if you're not sure, get your calculator out. Type in 0.8, raise it to a big power. 0.8 to a really big power gets really little.
Like how big?
Like 200.
Is it pretty little? 0.8 to the 200? Huh? Okay, so some of them will say 0, some of them will go to scientific notation and say e to a negative number. Remember, scientific notation, if you had this, is that a big or a little number? Little. When that exponent's negative, we're talking about little numbers, right? Think about it. 0.8 is 4/5. As you raise that to powers, don't you raise the top and the bottom? So the top is getting big, but isn't the bottom getting bigger? And when the bottom gets bigger, the fraction gets smaller. So if x is a really, really big number, this is 0. So your denominator, if that's 0, basically, it will never equal 0, but it's going to get so close to 0. This is basically 0. What does this fraction equal? 12 over 1, isn't it? So that asymptote is y equals 12. Now I know what your logical question is, and you should be asking this question. What if this were 14? Isn't the argument going to stay the same? Isn't that going to keep getting smaller, and so I'm just going to end up with 14? as my asymptote? So basically then, what we're saying is, next time I might not work all that out. Next time I'll know my asymptote is going to be 12 over 1. My top asymptote anyway. It will be 12 over 1.
It was like 12 over 2, and it's going to be like 6.
It'd be 6, yep. Now, we're setting our logistic functions up, so this is a 1, but I suppose we could have a problem where that wasn't a 1, so yes, then it would be that. Okay, now, other way around. What happens as 0.8 goes to a big negative number, like negative 200? Because if you raise this to a negative big number, doesn't that turn it over? And now the top is growing faster than the bottom. So this is getting humongous. Humongous times 2 is even humongouser. And then add 1. This is great big. So you have 12 divided by great big. What is that? Great small. So it's like 0. So if this is really, really big, then this fraction gets really, really small. The whole thing I'm talking about.
Yeah.
Which means that the bottom asymptote is at 0. Always. Because no number in here is going to change that except this one. Now, if this number is bigger than 1, the same thing is going to happen, but the curve won't be growing, the curve will be falling. But those asymptotes are never going to change. One asymptote's going to be at 0, and one asymptote's going to be at, in this case, 12 over 1. Now, I lied. You could change the asymptotes if you put like a +3 on the end, because what does a +3 on the end do? Pick it up 3 units. So the asymptotes would start in the same place, but if you had something like that, you'd have to lift the whole thing up. So they would be, in this case, they would be at 3 and 15. But that's the only way. That's the only way they're going to be different. All right, so A is done. All right, what about B? Where is the y-intercept in B? Well, how do you find a y-intercept? Let x be 0, so go ahead and do that and tell me what you get for your y-intercept.
3.
You got 0, 3, you got right, good girl. Okay, where are the asymptotes going to be? Well, one of them is going to be at 0, and the other one's going to be at 18. Wow, this is so simple. C looks different, but I don't want you to worry about it, because I want you to recognize that that can be rewritten as 9 over 1 plus 2, 1 over e to the x. So now look at that, look at the 2 that we just did. Is this number, I don't know what it is decimally, but isn't it a decimal? And now my exponent's positive, like this one was. So this is exactly the same. So where are my asymptotes? 0 and 9. Where is my y-intercept? Well, don't panic, because that's an e. When you make that a 0, isn't it gone anyway? Yeah, 1. So this one's also at 3. So that's a little bit about our logistics. We're going to spend more time with those soon. But try to remember this. This is our format. Remember, our format for exponential was this. When you are asked to write an exponential function, you're gonna find A and B. When you're asked to write a logistic function, you're gonna find A, B, and C.
Would there be like a way for it to be like for the top one, for example, like how it was the 12 over the 1 plus 2? Is there any way to make it where it won't be the top number is always going to be one of the asymptotes?
We said if you change this number,
Will it ever change? Because it's like the format?
not when we write our own, but could you in some problem, like we're getting ready to do some bacteria problem, could it be generated with a different number there? Yes. But it's always gonna be 12 over that number, or that number over that number.
Okay.
So it really doesn't matter if you throw in a different number there. All right, 7A, here we go, bacteria growth. The bacteria in a petri dish formula is given right here. 0.693T. Would you agree that's exponential? A is 100, and what did we say A represented? The initial value. So the very first question says, what was the initial number of bacteria present? How many bacteria were present? 100. We had 100. Our B, in our format there, our B is E. That's fine, 2.718, that's fine. How many bacteria are present after 6 hours? So we know we're starting with 100. We want to know, put them in the dish, feed them whatever you feed bacteria, and let them grow. How many will you have after 6 hours? Well, what do you think you're going to do? Jake?
Plug in 6 into T.
Exactly. Now, do we all know how to do this on our calculators? 100. Now, how do you get E? Anybody remember? Second ln. And as soon as you hit second ln, doesn't it give you like your exponent deal? So what are you going to put into that exponent? 0.693 times 6? Oh my. How many bacteria are present?
A lot.
Well, what's a lot? 6,000? I got 394, is that what you said?
Yeah.
6,394 bacteria. Let's not put a decimal on that, because we're talking about like
Whole bacteria.
beings, yeah. So it's like a people problem, we wouldn't want a decimal. We'll let the whole bacteria. Are you okay with that? By the way, this is an exponential growth problem. So if we graph it, that bacteria problem is, right, shooting up. All right, next. The amount of carbon-14 present after T years is given by this equation. Oh no, my eyes can't handle this. Negative 0.0001216. Is it 3 zeros after the decimal point? Yeah. How much did we have at the beginning of the problem? What was our initial amount? 20 grams, right? 20 grams, that's what we started with. How much is left after 10,400 years? So won't we just plug that in?
Yep.
So 20e to the negative 0.001216, 10,400. Don't worry about the negative exponent, it's fine, just type it in. So 20 second ln negative 0.001216 times all right, I got 5.65 grams. Did I type that in right?
Yeah.
When will the amount left be 10 grams? Okay, this is the last problem we're doing today, but it's a biggie. When will the amount left be 10 grams? Tell me how we're gonna proceed. This is our equation. What are we gonna do? Jake?
Set it equal to 10.
So
And like,
10 goes in for C. Would you agree? How in the world do we solve that? Drew? So one option would be the graphic. And if you were going to graph it, you would graph this as one equation, right? And this as another equation. And you would look where they cross. So one option would be to graph. Perfect. How do we do it algebraically? That is like with equations and
could
stuff.
you divide by 20 first?
Step 1, divide by 20. So that's going to give me 0.5 equals this. So 10 divided by 20, I put 0.5 because it's easier in the calculator than 1/2. Come on, you know this, I know you know it.
Do you have to like square root it to like to whatever that power is? Or-
No, because the T's in there. If
Oh,
there
yeah.
were a T in there, I might think about it, but
Yeah.
Katie?
You just put the whole thing under 1 because the fractions or the exponent.
Okay, now I could do that. That isn't gonna help me actually get T, but I could rewrite my equation that way, sure. Sure. Nyla?
Don't we like switch it to like, shoot, I don't remember. Isn't it like 5 to the E? Yeah, that's what I was thinking of.
Whenever we are solving for an exponent, we need logarithms. So I'm taking the logarithm of both sides. Because my problem has an E in it, I am using ln. There's two kinds of logarithms. We can do log logarithms or we can do ln logarithms. I'm using the ln because the base of that is E. Natural logarithms, common logarithms. Someone nod like, oh my gosh, I've heard that before, even though I don't remember anything about it. All right. So whenever your variable is the exponent, you're gonna logarithm both sides. I chose ln because the problem already had an E in it. And the beauty of that is, an ln and an E right next to each other cancel each other out every time. Every time you have an E and an ln touching each other, they're gonna cancel out. So ln 0.5 equals negative 0.0001216t. My job is to figure out t. So don't I just have to take ln 0.5 and divide it by this decimal?
Yeah.
That's it. That's t. So ln 0.5, don't forget to close the parentheses, divided by negative 0.001216 equals, I got 570.02 years.
When you put it in your calculator, would you click one and then plug in?
I put ln 0.5, close the parentheses, and then divided by that decimal. guys, that's awesome. You might get started on that 3-point homework, 3.1 homework. It's gonna be due soon. We're almost done with